right, today we are going to learn about limit properties and then we are going to apply them to more advanced limits. So we have three limit properties right here on the left and they kind of seem self-explanatory. Like the first one, if I have two functions that are multiplied together, well then the limit is just the limit of the first function multiplied with the limit of the second function, right? And the one under it, if I want to find the limit of two functions being added or subtracted, I'm going to take the limit of the first function and I'm going to add or subtract it with the limit of the second function. And then the third one, we're definitely going to do practice on the third one, but it's a composite function. So just talking about it, what we're going to do is we are first going to evaluate the limit of our inner function g of x, and then whatever that answer is going to be our new destination for our x on the outer function. Because you know how composite functions, they kind of switch like the inputs and the outputs of stuff? Yeah. So the thing is yes, these properties seem intuitive and they work most of the time, but there are some prerequisites. So for example, for numbers 1 and 2, you can only use those laws if the limit exists for both f of x and g of x at c. And then for the third limit law, that only works if there are two conditions. The first one is the limit of g of x has to exist, and the second one is f of x has to be continuous at the value of the limit of g of x. All right, so with these in mind, we're going to do some practice problems. Let's go to number 1. And so right off the bat, it is asking us for the limit as x approaches 5 of f of x times g of x. Well, my first function is f of x, that graph, and my second function is g of x. So the very first thing that I want to check is, at x equals 5, does the limit exist on both graphs? Okay, let's see. At 5, my limit on f of x is 1, and at 5 on g, my limit is -2. So yes, they exist for both of them. So now that I know that they exist, I can use my limit property, split up the two functions, rewrite it, and then just multiply. So I end up getting this. So just notice how I double checked to make sure that the limit existed first, and once they did, then I just really followed along with the property, and my final answer was -2. So I'm going to do number 2 now. This time it's asking about the limit as x approaches -1, but we are adding the two functions, so I want to check, does my limit exist for both functions at that designated value? So let's see, at f of -1, yes, my limit exists, and at g of x minus 2, so all that means is I'm going to plug in -1 into that value, so I want to see if the limit actually exists when it approaches -3. And it does, so that means I can use the limit property. And so once I fill in those values, I end up getting that my limit is 0. All right, how about you guys try number 3? So the first thing you would have checked is, do the limits exist at those values? They do, and then once you fill in everything, hopefully you should have gotten -9. All right, I'm going to do number 4. So this is a composite function, and the first thing we are going to do is determine if the limit of the inner function exists at that value. So does my limit exist when x equals 4? It does. Okay, great. And that limit is 0. Okay, and then what we also have to check is f continuous at 0? And it is. Great. So now let's put things together, and I get this. I know that the limit of g of x as x approaches 4 is 0, so then I take that output that I got on my inner function, and that becomes my new input for the outer function. So then it becomes the limit as x approaches 0 of f of x happens to be -3, and that is my answer. Okay, so these are all examples of when you are able to use limit properties, but now we're going to show you what you need to do when you can't necessarily use them because they didn't follow the necessary conditions. So our first function is a composite function. And again, the first thing that we need to check is, does the limit of g of x exist as x approaches 2? And in our case, it does, and that limit is 1. So now the question is f continuous at 1? And the answer is no. So because this question doesn't satisfy our initial conditions, we can't use those limit properties that we used in our first questions 1 through 4. So what we're going to do is we are going to go back to the idea of what is a limit in general. Remember, a limit, like the basic definition of a limit is, does the limit from the left equal the limit from the right? And if it does, then you have the limit. All right, so what I first did was I split this limit up into the left side and the right side, okay? And now I'm going to evaluate them separately. So to start the left side, I still have to apply composite properties to it, right? So what I'm going to do is I'm going to take the limit as x approaches 2 from the left of g of x and figure out what that number is. And when I do that, I'm just looking at the left limit for g of x as it approaches 2. That's going to be 1. So I know that this 1 is going to be my new input value for my outer function. But remember, f isn't continuous at 1. There is no limit when x approaches 1, right? So we have to go back and we have to determine what side or what direction we're coming from, because on this red section right here, I had a direction. It said as x approaches 2 from the left, and I got an output, but I kind of lost the direction. So we're going to go back and we're going to figure out what direction it is. So on the red section, it asked what was the limit of g of x as x approached 2 from the left. So you can see my red arrow right here. I am coming from the left of 2 to get to this y value of 1, right? Where am I reaching 1 from? Am I reaching 1? Am I coming from the top or am I coming from the bottom? Well, this arrow is coming from the top and it's going down, so that gives me a direction. So I'm going to put a plus right here on the 1 to show that it's coming from the top side. Okay? Then this will help us because now we have a new direction for our input, and now it's going to be 1 from the right. Okay? And then from there on, we can continue on with the composite function. So now that we added that little plus into our input, now we know what direction we want this limit to come from. Now it reads as, what's the limit as x approaches 1 from the right of f of x? And if I just look at the right limit, my value is going to be 1. Okay? So we did all this work. Wow, we only found the left side. Now we have to do it again for the right side, okay? So really, we're just going to do the exact same thing that we did to the right side from what we did to the left. Okay, this time it's asking for the limit of g of x as x approaches 2 from the right side. So if I'm coming from infinity to the right following this function, I get closer and closer to 2. What is that y value that it gets to? It gets to 1 as well. But again, with these composite functions, you need to tell me what direction is it coming from. So this is coming from the top direction, so I'm going to put this little plus right here. Okay? Then we know that this output becomes our new input. So we get the term, find the limit of f of x as x approaches 1 from the right. And again, we also know that because it's just one-sided limit, doesn't have to be continuous there. And we find that our answer is 1 for this right side as well. So we're going back to the basic definition of a limit. Did my left side limit equal my right side limit? It did, so that means that overall my answer is 1. Okay, I want you guys to try number 4 because it's really similar to number 1, so pause this video and try it out. Okay, so hopefully you recognize that the limit did exist when x approached -3 for g of x, but f of x was not continuous at whatever that limit value was. So we weren't able to use the limit properties. So we went straight back into going back to the basics of find the left, find the right, see if they equal each other. Okay, so I have it worked out. This is really what you should have gotten. And hopefully everything matches up. In the end, you realize that your left limit is 2 and your right limit is 1. And so because the two sides don't match up, for this number 4, your limit does not exist because your left limit does not equal the right limit. Okay, now we're going to do number 2. We're going to see if it satisfies our initial conditions, which is, do the limits exist for both functions? So does a limit exist for f of x as x approaches 1, and does a limit exist for g of x minus 5 as x approaches 1? Right away, I can tell that the limit does not exist as x approaches 1 for f of x because of this little jump right here. So I don't even need to check the second one. One of my conditions isn't true, so I have to check both the left and the right side now. So I am starting with the left side. And again, just like with the composite function, we still have to use those properties. So yes, I'm still using the property of splitting up my two limits, but because I am checking both the left and the right side, that's the reason why I can do it. So now I'm going to evaluate this. The limit of f of x as x approaches 1 from the left is going to be -2. And the limit of g of x minus 5 as x approaches 1 from the left is going to be 1. So those are my two values. I'm going to add them together and I get -1. And then we're going to do the right side. So these two values that I get are 1 and -2 respectively. So I also get -1 here. And again, we're going back to that definition of checking the left side and seeing if it matches the limit from the right side. And in this case, they both equal -1. So the limit as x approaches 1 of this function is going to be -1. All right, and now I want you guys to try number 3. It's very similar to number 2, but it's multiplying instead. But we've already done one of those, so why don't you try it out? All right, check my work, compare it to yours. Hopefully they're very similar, and hopefully they are actually the same because I'm hoping you got it right. If you did, congrats. That means that you really have this under your belt and you're picking it up really quickly. And if not, we're going to have practice. Like, I'm going to upload some practice problems for you to try out, and I'll put up the key as well so that you're not left hanging, okay? If we turn to the back of this page, we have the full list of properties of limits, and honestly, you're just going to be doing it the exact same way that we've done it. For example, the quotient rule right here, you're going to find the limit of the numerator and then divide it by the limit of the denominator separately. The constant multiple rule, you are going to take that coefficient out and multiply it by the limit at the end. The exact same thing goes with the power rule, so you can just take the power in the original function and apply it to the limit at the end. And yeah, so those are the only extra ones that we didn't really cover. So how about you try A? All right, and this is what I got. I recognize that there is a coefficient in front of my function, so I just pulled that 5 out, put it in the front of my limit, and evaluated it from there, and I got 15. Now let's do B. And keep in mind for B, you're going to have to use a combination of the sum rule and the quotient rule. So pause this video. And this is what I got, so just check over my work and then make sure you understand it. Okay, we're gonna go down now. Okay, there are two special trig limits that you just kind of have to memorize. The limit as theta approaches 0 of sine of theta over theta is going to be 1. And the limit as theta approaches 0 of 1 minus cosine of theta over theta is going to be 0. So you're really just going to have to memorize that. Okay, so now we're going to do some examples that use these special trig limits. We're going to start off with the first example. What is the limit as x approaches 0 of sine of 5x over 4x? Okay, the first thing that I'm going to do is I'm going to take out a coefficient. Technically, there is one. Do you guys see it? All right, it's going to be that 1/4 right there. So I'm going to use my constant multiple rule, and I'm going to take that 1/4 out and put it at the front of the limit. And remember, the only thing that I know are my two special trig limits, so I want to get what I have to look like what's in either that first or second box, right? So we're really close to looking like the first box, but the thing is my denominator is not the same as my input. So I kind of want a 5x on the bottom. How do you think I should get a 5x on the bottom? Well, I can do the same thing. I can multiply this entire limit by technically 1 disguised as 5/5. Okay, and then once I simplify everything, my new limit is going to be 5/4 limit as x approaches 0 of sine of 5x over 5x, and I know that that turns into 1, so my final answer is just going to be 5/4. All right, how about you guys try the bottom? I'll give you a hint. You're probably gonna have to split it up first by using one of the properties, and then try and see how far you can simplify. So what I did first was I split up the fraction, because that's just a property of fractions. They kept the same denominator. I could split up the numerator. Then I created two limits because I used the sum rule. And then I just evaluated and got my final answer as 3. All right, so after this page, all I have for you is just extra practice over piecewise functions and limits to infinity. So how about you guys try that? And thanks for watching.